Hello and welcome to yet another lecture on Basic Electrical Engineering, paper code ESEE101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today my topic is torque speed characteristics of separately excited DC motor. Lesson objective. After the end of this topic, students will be able to understand the torque speed characteristics of separately excited DC motor. So, in our previous lecture, we have seen that the torque that is generated in a DC machine that is directly proportional to phi Ia, that is phi is the flux per pole in Weber and Ia is the armature current. So in our previous lecture, you seen that torque that is generated in a DC machine is directly proportional to phi Ia, that is flux per pole, phi and Ia is the armature current. So today we will discuss the torque current characteristics of a shunt motor. So we have an idea that in case of the series motor, the field winding and the armature resistance both are connected in series. In case of the shunt motor, the field winding and the armature, that is field winding is connected in parallel with the armature, or that is called the armature resistance. So we all know in case of the, if I neglected the armature reaction, so if the field current IF is constant, the phi is nearly constant. So its torque that is proportional to Ia in case of the DC shunt motor, torque is proportional to Ia, that is means it is a Y equal to mx graph. So in case of the DC shunt motor, if we neglected the conception of armature reaction, it is clearly seen that torque that is proportional to Ia if phi is constant. So if torque is proportional to Ia means Y equal to mx. If I draw the graph or the characteristics of torque current, that is torque along the y-axis and current Ia in ampere along the x-axis, that is clearly seen in this figure. The torque current characteristics, it is a straight line passing through the origin, that is called y equal to mx, a straight line that is passing through the origin. So for the high value of the current region, if I go to the higher value of the current region, as the core became saturated, the TIA characteristics, that is T versus IA characteristics, that losses is linearity, that is seen in this figure. The T versus IA characteristics, that losses its linearity. So in the lower region, that is the lower value of IA, the torque is directly proportional to IA. That is the Y equal to mx. So for the lower value of Ia, torque is directly proportional to the Ia. But for the higher values, it is clearly seen that there is a Y equal to mx graph, a straight line that is passing through the origin. But for the higher value, the torque IA characteristics, that is losses the linearity as the core became saturated. So another part is the torque current characteristics of a series motor. So again, if I start that torque is proportional to phi IA. So in case of the series motor, that same current that is flowing through the armature resistance and along with the field resistance as they are connected in series, that is known to us. So we can write phi that is proportional to IA. So as a result, torque became proportional to IA square. So for the above equation that shows the torque versus armature current curve of a series motor that is parabolic in nature. Torque versus armature current graph or curve in the series motor is parabolic in nature. Now when the iron core that is get magnetically saturated, so the phi that is became almost constant and the torque that is became proportional to IA, that is the linear conception. So the both the equation, that is equation this one and this one, that shows that the torque versus armature current characteristics is a parabolic one at light or rated loads and straight line that is for heavy loads. So for the torque current characteristics of a DC series motor that is shown here, is up to rated load. The torque current characteristics is initially parabolic in nature, but finally it is linear when the load current that is became large. So initially it is parabolic in nature, then it is a straight line, become linear. So the characteristics that is relating the net torque or the useful torque PR of the armature current is parallel to the torque versus armature characteristics, but it is slightly below. The difference between these two curves is due to the friction and windage loss. Since the torque versus armature current characteristics of a DC series motor is parabolic in nature, hence the starting torque is high for the motor for a definite starting current because the torque that is proportional to I square. This property generally is used of a DC motor in traction motors. DC series motor in case of the traction motors, cranes and hoists, where the DC motor is to start with full load. High starting torque, that is as because it is proportional to the square of that starting current, helps to overcome the initial inertia of the load, and DC series motor speeds up smoothly with heavy load on it. This is the main advantage of DC series motor, or we can say it is one of the application of DC series motor. So let us another part, that is torque current characteristics of a compound motor. In case of the compound motor that we have discussed earlier, that it has both shunt and series field winding. So its characteristics are intermediate between the shunt and series motors. The cumulative compound motor, this is the characteristics of a shunt motor that we have known. This is the characteristics of a series motor, and this is the characteristics of cumulative compound, and this is the characteristics of differentially compound. That is the torque current characteristics. The cumulative compound motor is generally used in practice. So this is the torque in Newton meter versus armature current in ampere. The characteristics that is shown for a compound motor. So let us take an example that what we have learned from the torque equation, the formation of the torque. That let a 400 volt 6 pole shunt motor, this is a shunt motor that I have already told, but the field winding is connected in parallel with the armature, has a two circuit armature winding with 250 conductors. The armature resistance is 0.3 ohm, field resistance 200 ohm, and flux per pole is 0.04 Weber. Find the speed and the electromagnetic torque that is developed if the motor draws 10 ampere current from the supply. This is the supply and motor that is drawing a 10 ampere current. So P, that is 6 volt, Z equal to 250, armature resistance 0.3 ohm, and A equal to 2 because it is given that a shunt motor has two circuit armature winding. So R says that is the resistance of the field winding is also given, that is 250, that is 200, that is given. The field resistance, that is 200, that is also given. So now the phi, that is flux per pole, that is also given, equal to 0.04 Weber, and the current that is drawn by the motor is given 10 ampere, and the voltage V is given 400 volt. So what is the value of ISH? The voltage across it is 400 volt and the resistance is 200 ohm. So the current is 400 by 200, that is 2 ampere. So if the current that is entering drawn by the motor is 10 ampere, and from here the 2 ampere is going here, so means 10 minus 2, that is 8 ampere is the current IA. So IA equal to 10 minus 2, that is 8 ampere. So what is back EMF EB? That is Vt minus IARA, that is 400 minus 8 into 0.3 is 397.6 volt. So you all know that is EB equal to d phi n z by 60A. After putting all those values, the aim is find 795 RPM. So we have to find the speed that already found by us and the electromagnetic torque developed, that is the mechanical power output, electrical equivalent to the mechanical power output, that's EB into IA, means 397.6 into 8, that is 3180.8 watt. So torque we all know, that is EB IA by omega, where omega equal to 2 pi n by 60. So just putting those values, it is 83.21 rad per second. So the electromagnetic torque became 396 by using this formula, 397.6 into 8 by 83.21, that is 38.23 Newton meter. This is the way to calculate the torque of a DC. From that, for that particular problem, we have calculated the torque. So now we are coming to the speed equation of a DC motor. So we all know for a DC machine, the speed is, the back EMF is generally equal to P phi n z by 60A, but speed can be written by this equation 60A Pz into E by phi, 60A by Pz into E by phi. So where n, where that is E by, say this one is 1 by k, so that is n equal to E by 5, where k stands for Pz by 60A. So the equation shows that the speed of a DC machine is directly proportional to the EMF of rotation, that is E, and inversely proportional to the flux per pole phi. So the speed that is directly proportional to the EMF of rotation E and inversely proportional to the flux per pole phi. Since the expression for EMF of rotation applies equally to motors and the generators, it gives the speed for both motor and generators. Thus, suffix 1 and 2, that is denoted the initial and the final values. So we can write N1 equal to U1 by K into U1 by K into phi 1, where the N2 can be written as E2 by K into phi 2. So N2 by N1 can be written as E2 by D1 into phi 1 by phi 2. Now in case of the DC shunt motor, in case of the DC shunt motor, we all know that phi 1 is equal to phi 2 for the rated load condition. Thus, for a shunt motor, we can write N2 by N1 equal to EV2 by B1. Thus, for a DC shunt motor, we can write N2 by N1 equal to EV2 by EV1. So the another part is called the speed regulation of the DC motor. The speed regulation that is defined as the change in speed from no load, it is N suffix N L, to full load, that is N suffix F L, and it is expressed as a function of percentage of full load speed, and it can be written as, that is the per unit speed regulation, that is in NL minus NFL, N suffix NL minus N suffix FL by N suffix FL. So the percentage of speed load speed regulation, that is only to multiply this equation by 100. A motor that has a nearly constant speed at all the load, it said to have a good speed regulation. So the speed regulation is defined as the change in speed from no load to full load and expressed as a fraction or percentage of the full load speed. Now take another discussion in this lecture is the speed versus armature current characteristics of DC motor, that is in versus IA characteristics. So in case of the DC shunt motor, we can see that IS, that is V by RS, that we have already seen, if V is constant, IS will also remain constant. Hence the flux is constant at no load. The flux decreases slightly due to armature reaction. If the effect of armature reaction is neglected, the flux phi that will remain constant. The motor speed that is given by P is proportional to V minus IA RA by phi, that is equal to EB by K into phi. For phi that is remaining constant, that we have already seen, the speed can be written as in proportional to V minus IA RA. And this is nothing but an equation of a straight line with a negative slope. If the speed A of the shunt motor decreases linearly, if the increase in armature current that is shown in this figure, this is the speed in RPM, this is the armature current in IA, this is the ideal condition, there is rated speed at no load. And if there is a drop in IARF, this is a straight line. This is the practical condition of speed versus armature current characteristics of a DC shunt motor. That is seen that it has a negative slope, a straight line having negative slope. So since IARA at the full load is very small compared to the V, so the drop of speed from no load to full load, that is IARA, is very small. well-designed machines. The decrease in speed is partially neutralized by reduction in phi due to the armature reaction. Hence, for all practical purposes, the shunt motor may be taken as a constant speed motor because the drop of speed, that is IA RA, is very small. So we can comment that shunt motor may be taken as constant speed motor. So now let us take the speed equation for a series motor where A is proportional to V minus RA plus RAC. RA is the resistance of armature and RSE, that is the series resistance that is connected in series with the armature. So V minus RA plus RAC by phi, that is EV by K phi. So at the low value of the IA, that is the voltage drop, this part that we can easily neglect it. So N will be proportional to V by phi. As we know that V is constant, so N is proportional to 1 by phi. This is the speed versus armature current graph of DC series motor. So in case of the DC series motor, the field flux phi is proportional to the armature current flowing in the field winding. So we can write that in case of the series motor, phi is proportional to Ia. Hence, the series motor is a variable flux machine where A is proportional to 1 by Ia. Thus, for the series motor, the speed is inversely proportional to the armature load current. The speed is inversely proportional to the armature load current for this series motor. And the speed versus armature current or speed versus current characteristics of a DC series motor is a rectangular hyperabola generally shown. It is rectangular hyperabola. So the speed equation shows that when the load increases, the speed will be very large. When the load is decreases, the speed will be very large. Therefore, at no load or the light loads, there is a possibility of dangerous high speed, which means at the low speed, at the low value of the armature current, speed is high. So, for the no load or the light load, there is a possibility of dangerous high speed, which can damage the series motor due to large centrifugal force. Hence, a series motor should never be run unloaded. From the characteristics, it is seen that for a low value of the armature current, speed is dangerously high, which can damage the DC series motor due to a large centrifugal force. So, if for that particular reason, DC series motor never run unloaded. It should be always be coupled to a mechanical load either directly or through gearing. It should be coupled by belt, which may slip at any time, making the armature unloaded. With the increase in armature current, that is field current, the flux also increases and therefore the speed is reduced. So this is another is called the compound motor. So the speed armature current characteristics of a compound motor as shown in this figure, that is speed versus armature current. This is for the shunt motor, this is for the series motor, this is for the cumulative compound motor, and this is for the differentially compound motor. In differentially compound motor, it is that because of weakening of field, speed increases. If I go through the differential compound motor conception that we have seen in our previous discussion, because of weakening of the field, the speed increases. As the phase goes weak, the flux goes weak, and as a result, the speed goes on increasing with an increase in armature current that is clearly seen. But in case of the cumulative compound, when the speed drops because of increase of field flux with armature current, it is clearly seen in this figure the speed current characteristics of a DC compound motor. So another part of the discussion is the speed torque characteristics of DC motor. So first we will start with the shunt motor. Since the torque is proportional to the armature current that we have discussed in DC shunt motor, the torque speed characteristics of such a motor will be identical to the speed armature current characteristics. So this is the speed versus torque characteristics of a DC shunt motor, where the speed is in RPM, torque is in Newton meter. This is called the no-load speed, and it is identical to the speed armature current characteristics for DC shunt motor. Now, series motor. The speed torque characteristics of a DC series motor can be derived from its speed armature current, that is, and torque armature current characteristics. So the characteristics that shows that the DC series motor has a high torque, that is speed versus torque characteristics for DC series motor, and is derived from speed armature current and torque armature current characteristics. It is shown that for DC series motor has a high torque at low speed, and at a low speed the torque is high. When the speed is low, the torque is high, and when in a DC series motor has a high torque at a low speed and low torque, there is a low value of the torque at high speed. Hence, the speed of a DC series motor change considerably with increasing the load. It's a very useful characteristic for traction purpose or its needs, where at low speeds, a high starting torque is required to accelerate large masses that we have already seen. So another is the compound motor. So this is the speed torque characteristics of a DC compound motor. But the speed torque characteristics of a DC compound motor, a compound motor has a high starting torque. This is for the shunt, this is for the series, and this is for the cumulative compound. So a compound motor has a high starting torque together with a safe no-load speed. These factors make it suitable for use with heavy intermittent loads such as lifts, hoist, etc. This is the speed torque characteristics of compound motor. So this is the speed torque characteristics of DC motor. One is the shunt motor, followed by series motor, and followed by compound motor. So we have seen that how the speed torque and also the speed versus armature current can vary for DC motors or the DC machines, followed by the speed regulation conception. From the speed regulation, it is clear that a motor which has nearly constant speed at all loads is safe to have a good speed regulation. So the main focus that we have done today on the different characteristics, that is first one that we have obtained, that is called the the main part that is called the torque current characteristics or called the torque current characteristics of DC machines, followed by speed versus armature current characteristics, then followed by speed torque characteristics of DC machines or DC motors, and with the help of these characteristics, how the different motors are useful for different purposes or the applications that we have seen today. Thank you.